Good morning, folks. Ready to kick off our morning track sessions. As we said in the plenary, the tracks are focused on particular research projects, and this track is going to be focused primarily on digital transformation and digital engineering. So it's my pleasure to introduce Dr. Sousa-Poza, who will pronounce his name properly for you in just a second, from Old Dominion University. He's a professor and chair of the Engineering Management and Systems Engineering Department at ODU, and his research interests include complex situations, knowledge theory, decision-making, and planning and goal attainment in uncertain environments, which I hope we'll hear a little bit about here. He's going to talk to us about digital engineering implications on decision-making processes. So, Andre, good morning, and over to you.
Thank you. Good morning, everyone. Just going to go and thank you, by the way. I'm usually not allowed to speak when there's a time-constrained presentation. I tend to wander a little bit, and so what ended up today is a lot of material in a compacted space. I don't think I've ever managed to do that. So if we get to that 25-minute mark, feel free to throw something at me. All right. As mentioned, my name is Andre Sousa-Poza. I'm a professor of systems engineering at Old Dominion University. I'm actually very happy to see a lot of people here that I recognize. I think it's been a while. It's a little bit of a privilege for me to be presenting this work, and I really say that because this is actually a pretty broad effort that we've been working on at ODU. I am just one of the co-PIs. We've got two people that are really the leads on this work, and that's Dr. Kovacic and Dr. Shannon. Dr. Shannon is at the Naval Postgraduate School. Dr. Kovacic is a colleague of mine at Old Dominion University. And so this is actually a collaboration between the two schools, between the two universities, and we've been working at least this project through the SERC. So very specifically, the work that we've been asked to undertake has been to support the military Sealift Command in their efforts to basically integrate digital engineering into their decision support system, and I'll talk a little bit more about that in a second, just as I give you a little bit of background into the project. This turned out to be a very interesting project, and I actually appreciate a lot of the things that were said in the plenary speech just a minute ago. The complexities that this opened up were actually quite fantastic. The challenges, and so what. Beginning seemed to be, this should be a relatively straightforward thing. We're going to pop a whole bunch of sensors onto a whole bunch of machines, and we're going to port it in, run it all into some form of digital, and compare it up against a digital twin, use some form of machine learning, have the digital twins update, and presto, okay? And it's, right from the get-go, we started finding that this was not working out quite as it should, and so what evolved out of that is what's going to end up being a multi-year effort. Okay, and I wanted to mention that since as a multi-year effort, this is the first year of probably 4 or 5 years worth of work that we're going to be going on. And so in as much as this is, presentation is going to be a little bit of ongoing research, which I think is fantastic because that usually opens up the door for a whole bunch of very difficult questions that I may and or may not have an answer to, okay? All right, just as a real quick overview, and do I run my own slide? I guess I run my own slides here, no? All right. All right, maybe. There we go. See, I thought I broke it already. Thank you, yes. I was saying earlier, I broke Zoom at ODU yesterday, so if this is working now, we're still doing well. All right, so real quick, as a little touch of the background here, this project is being sponsored by, and the work is actually to support the Military Sealift Command. The Military Sealift Command is in fact one of the largest fleets of ships, not only in the United States but worldwide. It is a fantastic logistical enterprise, and they provide support to particularly float support to the United States Navy and U.S. Transcom. It is a revenue-based command. The reason I mention that is because, unlike the Navy directly, the military seal of command ends up having to balance decisions between what could we potentially do against what are the resources that we're getting. And so there's not just an effectiveness, there's not an indefinite effectiveness that we can work with here. They have to function with basically the trade-off of costs and efficiencies. Very specifically, we work with the military seal of command N7, which is actually the entity sponsoring us. N7 provides, they're responsible for providing ship maintenance. And so they do the vast portion of all of the maintenance planning. They have to make sure that the ships are functioning, that they're able to constantly support the mission, particularly the Navy and the other entities that they work with in the DoD. And maintenance turns out to be a really interesting problem to work with for the very simple reason that we're forever predicting things. And predictions are great because there's just this fantastic amount of uncertainty associated with everything that we do there. Particularly within the maintenance side, it becomes very interesting because we have this juxtaposition of perspectives that starts kicking in. From a maintenance point of view, we have a lot of work that has been done. A lot of things come out of the companies like Motorola in the early days when they started looking at reliability curves, and they were developing these reliability curves using millions and millions and millions of devices. They would test these against. And so we created this interesting notion, this interesting culture of the ability to predict when things are going to break, these effective lifespans, effective life cycles. That paradigm is fundamentally challenged, massively challenged when we start implementing it in an environment where we don't have huge runs, production runs, where we can define what these failure rates should look like, what these curves should look like, and when we start having to combine them. So all of a sudden we're looking at the reliability or the effectiveness of a ship, not just a ball bearing, okay? And so it creates a really interesting, an interesting area, an interesting place to sort of develop and for a lot of our research to work. The MSC, the Military Seal of Command N7, they actually do their jobs fantastically well, okay? One of the things that started driving us in the collaboration with MSC in this area is that they've been doing this for a long time. They're effective. They're really good at what they do. But one of the comments that was made is that 30% of the failures that take place were predictable. Okay, the other 70 is just this grandiose thing that entities like Military Seal of Command work at chipping away at, but fundamentally they become these random events. Highly uncertain, pretty much random events that become very impossible to predict, very difficult to deal with, okay? The work that we started looking at was how do we start changing the way we think about maintenance to start addressing more broadly, if possible, into that 70%, okay? And so it wasn't necessarily trying to improve the failure rate or the curves of specific entities, but rather from a planning point of view, how do we start reducing, how do we make the maintenance planning more effective? In other words, catch things before they fail, when necessary in particular, catch them before they fail, while at the same time not having this open door that says we can throw just unlimited amounts of money at this problem. Okay, and so those became the real nice trade-offs that we started working with. Right. Okay. And I'm supposed to follow these here because that was going to keep me within the 25 minutes. And I've already apparently lost my place. So there we go. All right. So typically speaking, no matter what we do, at the end of the day, what we're going to be doing with maintenance is trying to predict things. We're going to try and figure out when something should fail so that we can intervene before that failure takes place. And particularly if that failure is if we think that's going to be a critical failure that's going to, reduce the capability of a ship or the ability for MSC to deliver on the missions that it's supposed to support, we start looking at these very specific components, and at the end of the day, it becomes a predictive exercise, okay? The two dominant approaches that we typically have are typical predictive approaches which pre-calculate, they pre-estimate what the useful lifespan is going to be of an artifact, of be it a component, a machine, or whatever else. And then based on that, we start planning when we should intervene with some form of maintenance. Okay. Turns out that that is not particularly, it's not foolproof, because even within the useful lifespan, there is a percentage, there's a chance that things will fail. Okay. And so from a planning point of view, it becomes a little bit difficult. On top of it, some of these charts, these useful lifespan charts, are not necessarily always particularly accurate. In other words, when we have, again, cell phones, things that we generate millions of parts for, we can come up with pretty good estimates. When we start looking at larger engineered entities like ships, we don't have those production runs. And so there's one ship, basically the engine is supposed to be retrofitted usually every 15 years. Okay. The question becomes, why 15 years? Right? And one of the ships basically started overrunning past that 15 years, and there was no problems. There was no degradation in performance. There was nothing else going on. And so we have these stop ends that we wanted to work with. And so one of the basic ideas that starts coming in is that we can change some of the way that we do this. And one of the very typical practices that starts kicking in is that we start going to prognostic capabilities. And this became interesting because it starts resembling a lot of what we're trying to do within the digital engineering environment. The prognostic capability is quite simple. We start putting sensors all across the ship, which in many cases they're already there. Okay. And then we start making predictions based on that prognosis. Rather than saying this motor is going to last 10 years, we literally have a sensor on that on a device that starts telling us whether there's a degradation. Okay, this is actually not new. Back in late 1980s, I worked for a mine in Namibia, underground, about 2 kilometers underground. And my very first task as an intern, as a novice mechanical engineer, was to help basically put sensors on large pumps. Okay, middle of Africa, the one thing that we had abundance of underground was water. And you have these enormous pumps, you got to get that water out of that mine, otherwise you pretty much, you're going to flood the thing very quickly. And so these became critical devices, and my job was sticking thermocouples onto pretty much every bearing. Okay, and every day I'd have to go around up and down these blasted in the mine, pick up these temperatures and log the temperatures, so we could see whether or not we could start predicting when something was going to fail. Okay, so this isn't necessarily a novel idea. The technologies that we have now obviously advance what we're doing significantly. Okay, the tenet here though is prognosis. In other words, can we predict? Can we come up with a prognosis? Take the pulse of a machine, and from that determine whether or not something needs to be done. Okay. What we're doing is we're easing off on those predefined lifespans, useful lifespans, and we're hoping that we can get to a point where basically, based on this prognosis, I can plan when something needs to be, when an intervention is necessary. Okay. Both of these tend to work fantastically well on components. All right. The more complicated that we start creating an engine, a system, right up to the ship level, we basically have to start integrating all of these individual curves, all of these individual components, and it basically becomes a complex system. All right, the level of uncertainty that is generated when you combine all of these different entities is, it basically affects our ability to remain accurate or precise, or pretty much both of them. All right. One of the differences in what basically is being done right now is that, given the technologies that we've got and all of the newer technologies, artificial intelligence, machine learning, et cetera, they're already being implemented. They're already starting to be put in place. What we're really looking at with this digital engineering effort that we've got going is, in fact, to try and leverage most of these things. So what we're finding is that we can implement, this is out of literature, not necessarily with the military seal of command, but we can implement a lot of these techniques, but if we don't have a way to integrate them effectively, we end up with a lot of piecemeal solutions. We just end up with a much better prediction when my pump is going to fail, but very little that actually helps us understand how this takes place within the grander scheme of the ship's maintenance, okay? And so part of this digital engineering strategy that we're looking at is to see whether we can create a coherent construct. There's a construct that helps planning, and in this case, this is planning at the ship level, okay? Taking into respect that the ship belongs to fleet that supports the Navy, all right? And so we're really looking sort of at the ship level to try and understand how some of these uncertainties and some of these complexities start coming together. Overarchingly, this is actually an engineering effort, right? What the Military Sea Lift Command is working on is an engineering effort. Their intent is to come out with a maintenance decision support system that is augmented with digital engineering, okay? Just turns out that in that process, there are a lot of bits and pieces that have already been identified where solutions are not available, okay? And that's where, at least from our perspective, that's where we come in. We're the research arm to this engineering exercise. And so we end up picking up a lot of these tasks, very highly directed, even from the research point of view. Our purpose is to provide a way forward, solutions to this broader work that is being done within the Military Sea Lift Command. Our 3 projects that we started working on, although we actually had a pretty decent shopping list of things that we could start looking at, there's 3 areas that we're really working off. Now, I'm going to present them in the order here because I think I have better understanding of 1 and then of 2 and then of 3. And by the time we get to 3, that's actually Dr. Jiang Li's area of expertise. And so I end up deeper and deeper in the hole, okay? So there's not a specific reason why I put them in this manner. The first project that we started working with is we started realizing we need to come up with a theoretical construct, a new construct that bounds the problem space that fundamentally is capable of addressing the complexity, the uncertainties that are associated within the problem space. An associated project with this is we basically started looking at how the human digital twin interface, how that interaction starts taking place. I'll get into some of the interesting complexities that kind of emerge out of that space. It is very, very different to what we would typically, what we tend to address as from an engineering point of view. And the third project that we started working on, the Military Sea Lift Command, they actually work with a lot of chips that, in most cases, they did not buy brand new off the line, okay? And so, even from the point of view of creating a digital twin, this effort is actually first to create a digital library. Military Sea Lift Command still works with blueprints, okay? Some of those blueprints have been scanned, they're in PDF format, but they are still basically the original blueprints. They are, in fact, blue, okay? And so there's a third effort, and this is Dr. Jiang Li's area that he's been working on, is to support the work to take all of these manually drawn, manually put together blueprints and convert them into 2D vector files. There's 2 efforts that have been going on there. One is related to the actual drawing itself, and the other one has been to the focusing on the text, okay? Anyone that used to do drafting, we got put through the ringer, learning how to do the box lettering and so on. Turns out that we didn't all go through the same schooling for the drafting of those letters, and reading some of these things is especially the background noise has been an interesting activity. So I'm going to touch on these 3 just to sort of keep inside of the time limits. I could fill up 3 hours just on one of these, and so I'm going to try and keep it more towards sort of a purpose and sort of a status of where we're sitting. Right, so the purpose of conceptual bounding, like I said, is fundamentally we have got an unbounded space. This decision environment becomes an unbounded space in which, the notion of the alternative states, the possible outcomes, what we would look at in a more traditional sense using something like a Bayesian network or some basic classical statistical approach, becomes really problematic. We end up with pretty much this unlimited, undefined space, okay? based on some of the earlier work that we did, so going back 15, 20 years ago, one of the interesting approaches that I saw being taken is that we would often go into things like a scenario-based planning approach. And so all of these possible states, we would try to catch them as scenarios. And at some point, we started ending up with this incredible list of possibilities of things that could happen. And we would start lopping off pieces of this space, okay, because it's just too big, okay? And so, well, you know, if pumps fail, let's just ignore that. And this was really interesting in the security environment that I was working on, that we were working on back in that time frame, where essentially we would literally eliminate whole batches of threats. Entire threats would just disappear because we did not know how to deal with those scenarios, okay? Obviously, from a bounding point of view, it's not particularly satisfactory. It allowed us to then apply the traditional statistical approaches that we would have. At some point in time, you have to sit there and say, well, these states that I've actually captured might only represent 1%, 2% of the possibilities that come out of this. And yes, we've just created this perfect solution for something that, quite frankly, probably is never going to matter, okay? Yeah, and so the first piece that we started working on was within this conceptual bounding. And traditionally, we started referring to two different forms of uncertainty. The epistemic uncertainty, which is essentially a form of reducible uncertainty in literature. These are the ones that we can typically deal with traditional, with our classical statistical approaches. Simple rule usually is that the sum of the probability of all the states together is going to equal 1, okay? This is one of the basic rules that underlies things like Bayesian networks and so on. And that's what most of our current practices, in fact, most of the maintenance practices are still built on right now. We started looking at least from the space that we're working with, is opening that up. We need to be able to get into a broader environment where we're not bounded to a single outcome or a very limited number of constrained outcomes, okay? And so we started looking at both the sort of boundable, but anything up to an indefinite set of outcomes, okay? And then beyond that, obviously, we have the unbounded space, or the space might be bounded, but it's an infinite number of possibilities. That there becomes its own little beast. What you start identifying this boundary is that when we're going to get to a point where the number of states with uncertainty involved starts increasing, and all of a sudden we start seeing something that we refer to as an ontic uncertainty. Okay, and I'll touch those two words in a second. Interesting within this frame is that even the simple notion that the sum of all the probabilities of the probability of all the outcomes stops equaling 1. So we've got the interdependency between these states that basically creates a nice little bit of havoc in there, okay? And that's where our traditional classical approaches, our statistical approaches fail us, all right? From the way that we tend to work this is under our current practices, the bounding is defined by the inclusion of all of the necessary variability. So the discussion that came up earlier on, the idea of requisite variety. We need to be able, from our decision space, be able to capture at least what we're going to consider to be the relevant, necessary, requisite variety, okay? Understanding that, yeah, everything is interconnected, but we need to be able to capture whatever it is that we deem necessary. 99%, 99.9% of the variable, whatever it might be, okay? And we need to meet some form of critical space or some critical number there. We can't just start lopping, sorry, as an academic, I can, okay? I can lop off uncertainties and variables and all kinds of stuff because that's what we do, no? That's where we get perfect knowledge, all right? In practice, that doesn't work quite that way. And so we started looking at this next phase in here, which is this next space, which starts becoming basically the realm of possibilities. And goodness, and I'm on slide number 9 out of 29, goodness gracious. All right, so we basically get into the bounded, it is a bounded space of outcomes which start getting dealt with as possibilities, right? We refer to this the Realmöglichkeiten versus the Realwahrscheinlichkeiten, okay? Beyond that, there is still this space out there. We're not touching it. It's outside this open bounding, unbounded areas. All right. From a bounding perspective, essentially what we've started doing from the work, we have got our techniques. We've got these expected life, the operating age of some device, different shapes to these. Typically, they are relatively similar, okay? One of the simplest or first practices that we start doing is starting to look at just the variability that exists in the curve itself. Okay? And so one of the research projects that we are going to be working on is looking at how we aggregate these types of curves when we're actually also dealing with some form of variance in the curve itself, okay? Because that starts compounding pretty quickly. What we really want to get to is the graphic towards the right-hand side, which is really, when we start looking at the planning decision, one of the smallest dots that you would see right at the bottom, the component level, that's where this curve belongs. Okay, now we've got to figure out how we combine these, right? In a typical or a traditional sense, we know how to serialize them, we know how to put them together in parallel, and if the variabilities are not too big, we're actually quite effective at that. Even the simplest examples, we know that from process engineering, that even small percentages, when you start compounding them, our investment strategies, they get big very quickly. Right? And so we have to figure out how to get into the proposed practices realm, and the conceptual bounding essentially is it's the method that we've put together that help us differentiate between both the probabilistic and the possibilistic, and then we've got three more differentiations within it that we're working on. And the basic purpose is to help us align the methods, how we approach these problems, okay? So that we're actually applying the appropriate methodology, the appropriate techniques to these very specific spaces, okay? I want to get to this one, at least this one here real quick, even if I don't get to the last project. One of the reasons this becomes so important, again, going back to this idea of requisite variety, is that the moment we introduce the digital twin, or through this digital engineering, introduce the digital twin, we're basically connecting this fantastic data source, this immense amount of data, number of variables, through directly into your decision-making space, okay? And while that is an absolutely wonderful idea, what you have is the decision maker all of a sudden looking at astounding amounts of information, okay? And if we don't figure out what to do or how to do this correctly, it's probably going to have a detrimental effect. We're actually going to go backwards. We're not going to make any improvements with this. And so one of the areas that we started working on, and this is actually the area that Dr. Shannon out at the Naval Postgraduate School has been focusing on in particular, is understanding this interface. What happens when you integrate the digital twin? And so currently, the entire structure we have for engineering, for most systems engineering, is that we come up with this conceptualized idea of a system, possibly design, that ends up being realized, fielded, and we have this interaction, some feedback usually to this conceptual system. Did it do what we expected it to do? Okay. Within that, we have this idea that this fielded system, or the system of interest, is inserted into an environment, and we do a lot of work at trying to understand how that interaction works within that environment. The moment that environment starts becoming dynamic and ever more complex, we already start seeing problems, okay? The digital twin does a couple of things to us, right? The first is that this thing all of a sudden becomes a longitudinal problem. And so anything that we assumed was going to be nice and static, that we could define, like the environment, like even the field system, all of a sudden ends up becoming dynamic, all right? And our ability to represent these effectively, which was challenging to begin with, more often than not starts going to the tubes, okay? So this idea of representing an environment with enough fidelity, with enough accuracy, so that I can essentially tie my system design to it, okay, is difficult in the simplest cases. This thing starts changing, and we're assuming pretty much an open boundary here, this direct impact of the environment onto the system itself. What added to the complexity, in this case, on top of it, is that all of a sudden, through the digital twin, my conceptual system, or my decision space, essentially became part of that environment, okay? And, well, I can go back into some of the quantum notions, going backwards. Notions like Heisenberg start coming. This idea of the indeterminacy due to the effect of actually having your decision maker in the space, that we're going to be making decisions, right? So we basically have this influence that my perspective, my paradigm, every one of us as systems engineers, the way we look at this problem just introduced a whole new set of complexities. So every one of us could look at this with our unique take, and now we've got 40, 50 different paradigms to deal with, 40, 50 different potential solutions, most of which probably incompatible with each other, okay? And so Dr. Shannon, he's actually got a background in quantum, or actually in experimental physics. Before he became a systems engineer, he decided to get a PhD in physics before coming in and getting a PhD in engineering. What he's been working on is essentially introducing a quantum probability theory into this space. And this right now, I think, is one of the most promising areas that we have got to ensure that we create some form of coherent structure within this decision space after we've basically tied in the digital twin, okay? We had a lot of debate on this one because open systems had one meaning for me, had a completely different one for him. And so we've decided we're going to call this quantum open systems, okay, which is actually, in literature, it actually comes up quite frequently as quantum open systems. This is where this ontic uncertainty actually comes from. The ontic uncertainty is, in essence, due to the quantum states that are maintained. In other words, if we look at this from a systems engineering point of view, whenever we've got a problem that we would look at and say, well, it depends, okay? That becomes the ontic uncertainty. In other words, we're not sure which state is going to materialize when, when we start making a decision, when we intervene, okay? And so we have two different uncertainties functioning, and at least this quantum open systems theory, the quantum open systems model, is fundamentally what we're working with to underlie this, okay? And so the work that we're looking at here is to augment our decision space with this open system model, open systems models, and yeah, if anyone's interested, both report, or if you want to contact me, we can go into this, and I'd love to go into this in more detail. But essentially the tenet here is to be able to develop a space where we're able to maintain possibilities rather than just a lot of components. Okay, how do we bring these together? Just as a caveat, what we're looking at here is not quantum machines, it's not quantum computing, it's quantum-like machine learning. Okay, and I think again, based on the previous speakers, where you replace the processor, the controller with a AI, this is fundamentally the tenet that we're looking at here, is in this loop between the decision space and the real artifact. What we're looking at is the introduction of essentially a set of heuristics built on this quantum open systems models, okay? Basically to evolve the probabilities. All right, like I said, last project is this blueprint idea. And here, what I'd like to do is just two pieces. There's a lot of work that went into this. Turns out that it's a lot harder to read, but I wanted to highlight some of this. After a lot of work, two things came up is Dr. Lee and the people he's working with came up with a mechanism to actually come up with a pretty decent reading of the block lettering that we should all recognize as drafting and engineering. And through the two different mechanisms that he's put together with both pre-train and then fine tuning, he's actually getting extremely high accuracy levels. Okay, so 92% and individual characters at about 97.5%. Okay, one last graphic here. So also on the drawings, use two different approaches, using a generated and a discriminator to come together. I'm just going to go on to the results here. Just to sort of point out what happens when you have a graphic. This is actually the blueprint on the original image side, and then the cleaned up image is what comes out of this machine. And it's picking up the graphic pretty well, but even there you notice that there is noise, okay, that remains inside of these pictures. This is just another one of these factors. There's another area where we start dealing with or battling with digital engineering, is that there is an astounding amount of noise, variability, data, information that is coming in to this space. When we start looking at this entire set in a combined manner, the uncertainties that are generated are actually, they're astoundingly high, okay? And so really one of the big challenges that we're looking at from the point of view of what we can do with digital engineering one of them has to be, how do we manage all of these uncertainties, okay? Because if we can't do this in an integrated fashion, what we're basically going to end up with is, yeah, not much better than what I was doing, sticking thermocouples onto the side of pumps, okay? And so I think there's a big challenge here. Like I said, work in progress at this point in time. All right, 25 minutes? Oh, wow, man. I hope it was recorded. This has never happened before.
It was recorded.
Yeah.
So, do we have any questions for Andre? Questions about this? While you all are coming up with your questions, Don will come and bring the mic to you. But I did have one question, and that was, you talked about parsimony or requisite variety. You can't include all scenarios. How did you all go about making those decisions about what you're currently including versus excluding?
Good question. All right. So the biggest battle that we start dealing with is right over here, okay? I mean, at some point in time, the real movement that we've got is under the current practices. Basically, we're implementing those using classical models that are based on classical probability theory. Anything from Bayesian networks to just our basic processes or typical process control. When we start moving into this next phase, what is defined by the Zontic uncertainty, the model that we're building out is, it's actually based on Hilbert space, which, at this point I have to be cautious because that is where Dr. Shannon gets his strength from, no? But basically the Hilbert space is it's an interesting construct that would take what we would define under our typical Euclidean spaces and puts it into an n-dimensional space where the space itself, quite interestingly, can warp, okay? Hilbert space generates what physicists refer to as a complete representation. In other words, it's able to maintain any perspective that is introduced into it in a mathematically sound manner, okay? Now, that word complete can be a little bit deceptive in the sense that it is complete from what we would have inside the decision space. Is not complete from the sense of everything that could possibly happen in reality. And so we still got that that dotted area, this unbounded domain. At the end of the day, no matter what we do, we still have to figure out where a bounding exists, how that bounding exists. So how would we do this? Right now, the notion, the theory, what we intend to work on is that using something like the Hilbert space or Hilbert space construct, we start introducing different perspectives. The perspectives start defining the breadth of that space, okay? What I cannot answer at this point yet is where that dotted line would lie, right? And so if we fail to capture perspective, we're still missing something that could potentially be in the space. Good question, don't have a good, fantastic answer on that one yet.
Any further questions,
Thank you for the very nice talk. And my question is, I guess one thing that we've observed in doing work in the prognostics and health or condition-based maintenance space is that when we build AI models for predictive maintenance, and actually use those models to do something like perform maintenance as the basis for the decision to, say, change out a part, then in certain situations, what we end up doing is destroying our models without the capability to bring them back. Yes. Because we've effectively created a new system. The repaired system might look in a macro sense very much like what you started with. But for the subtle correlations that are used for for some of these predictive maintenance problems, it can end up being destroyed, and there's no opportunity really to get the model back without the kind of training that might have gone on over a long time period. So operationally, it's a problem. But I guess what I'm trying to speak to is whether you've also observed any kind of entanglement in the digital twin sense between the health of the AI and the health of the system, and a need to, to have those moving in lockstep.
We haven't observed it because we haven't got to try some of this out yet. But this actually has come up. It is one of the elements that has been hypothesized. It is something that is going to have to be dealt with. The problem with basically with the idea of digital engineering, the digital twin, is that, again, this digital twin ends up becoming part and parcel of the space itself. And so you have, the word is entanglement. Okay, from the quantum spaces comes the entanglement. Every change, every decision that we make, fundamentally needs to start changing or affecting the entire the digital twin, the model that we would have. And there is no real way to do that. Okay, where we start seeing this is if you have a brand spanking, I'm a mechanical engineer, I like the idea, you have a brand spanking new pump machine, whatever it is there, and you start working on it, we can actually, we run our calculations. It's part of what we do in the design phase to begin with. Now, what happens when we start making changes to that machine? Right? The entire set of calculations that underlie that everything was based on, all of a sudden ends up having to be put in question. So now we switch out the bearings, but in doing so, we did not switch out the impeller, the shaft, and anything else. That shaft and everything else is going to be under certain pressures, under certain forces that weren't in that design. They're new. Okay, how do we update the way that design would work, that digital twin would work? Okay. Yes, good one.
The question of should we change the system design in some way to accommodate a robustness with respect to digital twinning or our AI models that are the basis of decision making. I think that's a frontier where we could ask, okay, let's change the design, let's make it modular, the repairs more modular. Let's change the training for the person who has the wrench so that it's a torque wrench instead of just a wrench or whatever. So I think we also get entangled in the idea of the design, right? Of can we actually design for digital twinning, or for for AI-based support in the future, or design for the support of the AI is another way of putting it.
Comment was made earlier on. Do we start allowing our AI to design software and then run it? And in the same sense, within the digital twin, we start getting to the point where, where literally it's the digital twin starts driving our design. Okay, in a purely informational space, it actually becomes an interesting philosophical question. Okay, in a space where we're combining essentially a physical artifact, a ship or something else, there are, I think, really interesting elements to that, because at some point in time, whatever we are injecting or introducing within that decision space is going to come bouncing up against reality. Okay, we've tried to do this in let's call it a more manual way with the notions of agile. At some point in time, it's great for me to say agile, but I just laid the keel of a ship. Great. Okay. Are we going to be making changes? No. And so we start with basically an entanglement. We start with basically these two pieces, these two entities coexisting in the same space. And to what extent do we start allowing the digital artifact, the digital twin, whatever we want to look at there, and the AI and everything else associated with it, defining our reality for us? Okay. I know that in control systems, we've had some very interesting problems arise from that, where, for example, in the automation of cockpit of control systems in aircraft. At some point, the digital twin is making putting wonderful ideas together in a virtual environment. They don't work that well necessarily when we put them out into reality. And so, yeah, I think there's a lot that we can learn going back to nature on beyond the requisite variety, the homeostatic capabilities that need to exist within this. Okay, how do we contain? It goes back to the bounding questions. How do we contain what we're literally doing within this space?
All right, Andre, thank you so much for your presentation. Unfortunately,
No more.
yeah,
I'll be here. Thank you.
thank you so much, and we